Bueno, muy bien, pues voy a presentaros el ponente de hoy, ¿vale? Yo lo voy a presentar en castellano, él va a dar la charla en inglés, ¿vale? Y, en fin, es un investigador, un colaborador también mío, se llama Leonardo Scarabelli, y tengo aquí una serie de notas sobre su currículum, ¿vale? Leonardo es químico de profesión. Estudió en la Universidad de Pavía, en Italia, y ya al terminar su máster se vino para España y empezó su doctorado con el grupo de Liz Marzán en la Universidad de Vigo, que como, bueno, no sé si muchos lo sabéis o no, pero es una referencia a nivel mundial en el campo de la plasmónica, ¿vale? Del estudio de las propiedades plasmónicas de nanoestructuras. Entonces leyó la tesis en el 2016 y posteriormente realizó una estancia postdoctoral en Estados Unidos, en UCLA, y regresó al Instituto de Ciencia de Materiales de Barcelona, que es allí, por cierto, donde lo conocí, donde estuvo trabajando y trabaja hasta ahora. De hecho, en un mes se muda y comenzará su estancia, digamos, como ya, bueno, tenor en la Universidad de Cantabria, ¿vale? Donde además le han otorgado, bueno, el European Research Council le ha otorgado una beca RC, una Starting Grant. Leonardo es un experto en el desarrollo de síntesis, de métodos de síntesis de nanoestructuras con propiedades fotónicas y plasmónicas para estudiar, digamos, aplicar regímenes de weak y strong coupling a desarrollar propiedades no lineales, y también pues ahora mismo está centrado también en su aplicación para temas de fotocatálisis, ¿vale? Y creo que es un poco lo que hacia el final os contará, ¿vale? Así que nada, no me enrollo más. It's all for you. The dance floor is for you.
Well, so I'm going to switch to English for the talk, but feel free to ask questions later on in Spanish. It's totally fine if you're more comfortable with that. So thank you for the introduction and for inviting me here. So today I'm going to cover a little bit, I'm going to start from a little bit of introduction on plasmonics in the general field, in case some of you are not familiar with it. But then I'll move a little bit into what we do more recently, what I look into in the ICMA. And then by the end, I will close with a little bit different perspective on a new approach that we've been developing very recently, and that is what basically will constitute at least the main research direction in the University of Cantabria with the ERC. So just to give you a general introduction, very general, the plasmonic properties, so why we are interested in colloidal metallic nanoparticle, is because when these colloids become smaller than the wavelength of the light interacting with them, their electrons start to oscillate when they are exposed to light. And this generates a strong absorption and strong interaction. And the reason we are interested in this is that not only they generate a resonance, the so-called localized surface trapping resonances, but these also come associated with very strong electric fields in the proximity of the metal surface. And so we can use these interaction as plasmonic sensing. So basically these oscillations are sensitive to the chemical environment. So we can use them to do some sensing, but we can also use these excited electrons, these oscillating electrons, for doing catalysis. And then finally, once the electrons are excited, they will relax. Okay, as it happens with molecules, but instead of doing it in a radiative way, so fluorescence, just to be clear, in this case, the vast majority is basically relaxed as in light to heat conversion, and this opens the field of plasmonic photothermal therapy, for example. So there is a lot of interest in this type of structures, and so the chemistry and in colloidal chemistry, we got very, very good at tuning this plasmonic response. So basically it turned out that the response, so this optical response of the nanoparticle can be modified, changing the nanoparticle size, as you can see here, red shifting, so moving towards lower energy when the particle gets bigger. We can play with the shape of the particles, and again, tune the response. So for example, here you can see the case of the nanorods, that being an elongated sphere will have two types of response depending on the orientation of the nanoparticle with respect to the light, that we will have a longitudinal plasmon and a transversal plasmon. But we can also play with the composition, making bimetallic or multimetallic structure, and this will again change the optical response. So basically this can be summarized a little bit in the slides. That is basically my life as a PhD student. So when I did my PhD, it was all about making this very nice particle. We developed some synthetic methods. We had fun seeing where the plasmonic response was localized on the particles, and so on and so forth. So now we really reached the point where changing the parameters that we use for the growth of this particle, we can really finely tune how big they are, the composition, the shape, and so on. And so we got very, very good at this, at least for gold, silver, and the main metals. There's still a lot of work to do for other compositions. But again, my life as a PhD student was alive. In the sense that, of course, localized surface, everything comes with some drawbacks. And in the case of localized surface plasmon resonance, the problem is that these resonances are associated with a lot of optical losses, which basically means that these plasmons are very short-lived. They live for a very, very short amount of time. And this basically translates at the end of the day in low quality factor. So you can imagine a quality factor has visually, like looking at this, invisible extinction spectra, where you're looking at very sharp signals, while localized plasmon resonances are always quite broad. This is fine for certain applications, but it's not for others. So if you talk to a physicist or a botanic person, will tell you that these are not very exciting resonances, but they want better resonances. And so basically, how can we improve this? And so to do this, there's going to be like 2 or 3 slides that are going to have some equation in it, but I'm a chemist, so I will keep it very simple. Basically, we can try to approach this problem going into the coupled dipole approximation theory, which basically says my nanoparticle is a dipole, is an oscillating dipole, okay? And so this oscillating dipole will respond to the external electromagnetic field following, and I can basically describe my nanoparticle through its polarizability. Okay, so it's a very simple equation, as you can see. Now, if we use this equation, we can simulate the response of the nanoparticle. But now, what happens if I have more than one particle? So what I can do is saying that every single particle will not only respond to the external electromagnetic field, but will also respond to every single other particle present in the system. Okay. So I can simply write an interaction tensor and says, okay, here I have all the perturbation. Okay. If we analyze this type of system, again, this is all numerical, but it serves very well our purpose here, is that we see that there is an interaction within the particle that depends on the distance between the interacting particles. And if we get very, very close, we see that the response changed dramatically. Okay, I can make a dimer here, but I can make a more complex system. But basically, the take-home message here is that we can identify 2 regimes of interaction. One is a near-field coupling, the so-called near-field coupling, where the nanoparticles are very, very close one to the other. This is very useful because there is going to be a strong perturbation of the optical response, but this is going to be associated with very high electric fields, this so-called hotspot that we use for enhanced spectroscopies and so on. This is very interesting, but from the perspective of someone that wants to have very high quality resonances, it basically doesn't work, because what you have is extreme light confinement that is also associated with much higher optical losses, which again have much broader resonances. And if we go to the other regime, this is a far field coupling where the nanoparticles are very far away, and this is generally negligible. So there is basically no effect. And so this is always something that is pretty much not considered. However, if we look at this a system where the nanoparticles are organized in an array, then things changes a little bit. So the first thing that is very important consequence is that we can simplify the math, which I always appreciate. So we can basically get to this kind of equation where we see that the conditions for the resonance, so for a maximum value of this number here, are found when the polarizability and the tensor have a specific they're basically similar one to the other. And this is a new set of resonances. because they do not only depend on the polarizability, but depends also on the lattice, so on how we dispose this nanoparticle in 2 dimension. So as you can see here, the effect at the end of the day is that I will have very, very sharp optical features. This is, again, simulations. And this gave me a new set of resonances, of plasmonic resonances that are called lattice resonances, because they emerged from a lattice of particles. And this can solve basically our problem. And so one way that you can see this is that now, when you move away from your reference particle, that in this case is here in the center, I move at a distance d from it, I will include d squared dipole. Okay, so if I move to one distance, I include more dipoles into my system than the decay of my system. And so basically at the end of the day, what this is telling you is that all the localized plasmon of the particle interact with each other in phase in certain conditions, the one described by the denominator there. And this basically end up with having plasmons that are delocalized. So basically the entire, you can imagine it as the entire array oscillating in phase. Consequently, you have long-lived plasmon that have very sharp features. So basically, the take-home message here from these little introductions that if we manage to arrange plasmonic building blocks into an array, it should be a very convenient way to overcome the optical losses of the system. So other take-home message that you should keep in mind for the rest of the talk is the first one is that these are new type of resonances, and that depends. It basically come from an interaction of the localized resonances with the array. And this means that I can change these resonances acting on both the components here. So I can change the resonances by changing the polarizability of a single repeating unit. So basically changing the shape, the size, and the orientation of the particle. But I can also change these resonances by changing the geometry of the system. So as you can see here, I can have a more complicated response. And then finally, that since there is a diffraction component here, there is an array, okay? These resonances are angle dependent, so will depend on the illumination angle that I use to illuminate the system, okay? And so you can see here basically how these can change, and of course they are also dependent on the chemical environment. So traditionally, these structures have been fabricated using nanofabrication techniques, so electron beam lithography and metal evaporation. And this has been very great for understanding their optical properties and studying the system, understand how they behave from a physical and optical point of view. But lately, the field of metamaterials has been moving to a new phase where people start to look at, okay, can we use this to do what they call the chemistry of metamaterials? So start to use this system to interact with the chemical environment and, for example, use these resonances to run reactions, do photocatalysis, or things of that sort. And here you create a problem. The problem is that when you create a system an evaporation of the metal, you don't have so much control on the crystallography of the system or on the quality, basically, of the structure itself. So there is an interest. This creates an interest in using bottom-up colloidal nanoparticles to create the kind of structure. Because with bottom-up synthesis, we can not only control the morphological, as I showed in the beginning, but we can also control the crystallography, the components of the system, and create very complex structure that you would not be able to fabricate using top-down methodologies like beam lithography and so on. So how can we integrate what we know how to do in solution, so colloidal system, directly for the fabrication of metasurfaces? So the first response is, which is going to be the first part of my talk, is we can use self-assembly. And there are many different techniques, but I will focus on templated self-assembly, which is the one that we use. There are, just so you know, many other options, like capillary assisted and electrophoretic, but there are many others. And so this is a field that have been looked into for quite a long time. But this started during the end of my PhD with the group of this Marsan, and when we started looking at how can we assemble these particles from the solution. This is what you see here is by simple drop casting. Then we move to templated self-assembly, where we basically dry this nanoparticle confined within a structure that has a certain stamp, that has a certain geometry. So we can create this kind of let's say, of architectures. And then we, more recently, this has moved to the nanoscale. So now we can create these type of structures where you start to have nano architectures that enters the nanoscale, and so we start to see a response, a complex response. So here, as you can see, by changing the distance between these array, we can move these lattice plasmons in different. Again, these are not very exciting because these are still broad. Okay, we always want something sharp. And so how can we look and try to understand how can we make this narrow? And so this is when, by the time I arrived in ICMA, this is basically what we started looking into. So the first thing we did was, okay, let's take this nanoparticle, let's make different lattices, and let's look what we get. And so again, this is the optical response that we got. We were not very happy about it, but then we decided to do a full optical characterization because this is only with basically your sample and you illuminate from normal incidence. So now we tune the angle. And so what we started to observe is that if we look at the diffraction line, there is a specific angle where the diffraction line crosses the response. So in those conditions, you start to see very sharp features. However, this is not optimal. So basically what you're seeing here, the conclusion is that this blue line that you see here is not the lattice resonance, but is basically the response of these clusters over here. And then overimposed over that, there is our lattice resonance that appears at certain angle. And so we start again asking the same question. We have the motivated us, which is how can we achieve lattice resonances? So we started, the first thing that we came up with was, okay, let's change the composition of the repeating unit. And so in this work, what we did was changing the dimension. So the idea was, okay, here the problem is that the near field coupling within every single cluster makes my resonances so broad and increase the optical losses of the system that then I'm not able to, let's say, bring down the optical losses and see my sharp lattice resonance. So let's make the particle bigger so that my cluster will be ideally made by single particles. And this worked to a certain extent, but basically what's come down to is templated subassembly is not extremely good at positioning single nano objects. As you can see here, the lattice is not very precise, and this ended up basically losing the quality of my optical delocalized response. And so we tried to go in the other direction, basically making my particles smaller and integrating more particles. And so we started to see that also going towards smaller particles, we started to see some sharp features, and so we started to understand why. And it turned out that basically moving away from these conditions, which is the first one that I show you, where you have strong near-field coupling, you can move into the other two conditions where you have weak near-field coupling. And this seems a little bit counterintuitive, but basically when you have very, very small particles, the near-field coupling is also much lower. So at the end, if you look at the response, the near-field coupling is lower in either sides. But unless, so this one, where you have very big particles and you try to put one particle for each position of the array, this is very hard to do with our technique of templated self-assembly. Instead, this one is very, very easy. So by coupling everything that we knew, we basically optimized the system. And in this first work, we were basically able to arrive to, this were the best one that we found, where basically we have sharp resonances around 60, 50, 60 quality factors, which is just a number that tells you how sharp your resonance is, okay? So typically localized resonances are below 10, and now we start to look at things that go towards, above 50. Well, this is again showing you a little bit analytical. This is a simulation where it shows you that when you go from a perfect system of single nanoparticle, you start to create defects and move particles around. That is a very, very quickly this becomes a very much detrimental effect on your collective response. In the second work that we did was okay, let's try to exploit this. So now we know that how else can we modify the internal structure of these nanoparticles of these clusters array. So one thing that we thought this was a work that we did for with a master's student was basically let's try to mix particles together. So we synthesized gold and silver nanoparticles. In this case, they were quite big. They were 50 nanometer. The motivation for that will become clear a little bit later in a few slides. But basically, we just synthesized the two colloids and then we co-assembled them. So we did exactly the same procedure. So we dried these under a stamp. And this is what we got, and we saw that we can we see the effect. So the more silver we have in the system, the better the response. This is expected because silver has better plasmonic properties compared to gold. But what we were interested was in let's see what happened if we heat up the system. So the idea was we heat up the system and then we melt the particle together, and these would basically create a single structure. And so what we were interested in is, here you see the case of gold, where you improve the properties, because we indeed create single structures, so we make the resonance a little bit sharper, while with silver, we have the problem that silver tends to oxidize or anyway go, and it's a less stable metal, especially when you warm it up. So we ended up creating the structure that were actually worst. But the real thing that motivated our study was to try to create bimetallic system. And at certain conditions, specifically at 300 degrees, we were actually able to put together both gold and silver and create particles that show patchy elemental composition. So this is not a complete, you're not alloying the system completely, but you still maintain the presence of a gold area, enriched area, and silver enriched area, which depends on the composition, of course, on the initial composition. The thing that is very interesting here is that if you look at the optical properties, we see that the system that contains a mixture, so just a 25% of gold basically is enough to avoid deformation of those items that you've seen in the previous slide for silver. And so we are actually able to improve the optical properties. We also try to push the system to the limit, in this case, increasing the temperature. And what happened in this case is that we have completely alloying of the system. So this is a bimetallic. The two elements are equally distributed within the structure. And then once again, we observed that we could get quite sharp resonances. These are not as high as the one before. This is probably due to the fact that here the particles were bigger. We think that maybe using smaller particle, we can actually make the system better. But the resolution of the EDX basically was the limitation here. So with smaller particles, we were not able to observe this type of system. So this is a little bit something that this has been a very brief project, but we are interested in maybe alloying together more interesting metals, which could be interesting, as Juan mentioned in when he was introducing me about for creating photocatalysts, combining the basically optical properties of noble metal like gold and silver with the more interesting catalytic properties for other metals. It's not mine, right? No. Finally, what I said at the beginning is that we can also work on the general architecture. So now we have a metasurface, as plasmonic metasurfaces, that is also sensitive to the environment. So one thing that I forgot to say when I was introducing the lattice resonances is that in order to have this communication between lattice, you need the particle, the single unit constituting the array, is that you need what we call an homogeneous dielectric environment. So basically, you need your nanoparticle to be within one media that is the same. So normally what we do once we deposit the particles, that we cover them with another layer that is matching the glass, the refractive index of glass. So these systems are isolated. This is the only way to see the lattice resonance. When Ili, that is my PhD student, joined the group, we were interested in looking at in leaving the cavity, so leaving the metasurface open, because otherwise there is no way to access the chemical space of the surrounding environment if the particles are trapped within in our case the PDMS layer. And so what we did was basically create a thin film. In this case, containing rhodamine B, because we wanted to look at how we can use this plasmonic metasurface to modify the fluorescence of the rhodamine B system. And so we created a thin film of around 250 nanometer of these is SU8, so basically it's a photoresist containing the rhodamine B. And then we create our metasurface on top. As you can see here, this is how the sample looked like. And these are just zoomed in picture where you can see the cluster. These are 23 nanometer silver nanoparticles. So as you can see here, we did the same optical characterization that I explained before, so changing the angle, so we could see these very sharp resonances that move. And interestingly, all this is done without embedding our metasurfaces in a PDMS layer. So these are all open cavity. So we dug a little bit in the literature, trying to figure out why we could see these sharp resonances without embedding the system. And it turned out that what's going on is that we have some waveguided mode. And so you have an hybridization between our plasmonic response with the waveguide mode. And this basically allow for the emergence of these lattice resonances even without the matched supra layer. And so as you can see here, again, the values are pretty high for colloidal system. Of course, there are in the literature higher, but these start to be nice resonances from a photonic. And so we decided to see basically how we can modify the emission properties of rhodamin B using this strategy. And so the idea was to create a lasing architecture. And so basically here, what you're seeing is exactly the same representation of this. Okay, so what you're seeing is the diffraction line. This is just a different representation of the same thing. But what we're interested in is that when this diffraction line crosses, so we have an area that has a lot of diffraction lines coming together. Basically, that is a good point to look to promote lasing activity. So in this case, it's here in the center, and the way you look at this graph, this is a K-plot, but basically the way you look at this, that this means normal incidence or normal emission in this case. So the idea was we pump the system from the top, and then there should be this interaction, and the rhodamin B should start to emit normally to the surface. So this is the theoretical prediction. And this is the experiment. So basically, we confirmed the way we then analyze the emission, and because there are other processes that can explain these very sharp emission, and so we basically, to make sure that it was lasing, we first of all look for a threshold behavior, and then we look at the divergence. So if it is lasing, it should be as you can see here, 1 or 2 degree in distribution. So if I move the detector away from the sweet spot, I should stop seeing lasing, as you can see here. And then finally, we look at the polarizability, the polarization, sorry, of the generated light. And this is the prediction is the red one, and our data are the black spot. And I'd like to remind every time that I present the slides that all these points that you see here in all these 3 characterizations were taken from the same spots. So the system is actually quite stable. Compared to other systems that photo bleach, and this is possible because of the relatively low threshold. This is for people that work in lasing. This is when I say low threshold, they give me very angry looks. But let's say for a prototype system using colloidal metasurfaces, this was we were actually pretty happy with this value. And so then, as I said, this system is very versatile. So we start to say, okay, what happens if I change the lattice parameters? So in this case, I'm changing the lattice parameters. So I'm changing all the properties of the plasmonic and optical properties of the system. And so what happens is that now I should expect a lasing activity not at the center, so not coming out normally, but I expect it at a certain angle. And so what you see here is that it's basically represented here, right? I should illuminate from the normal direction, and I should expect my lasing coming out at an angle. And so what angle? Well, basically every circle that you see here, concentric circle, is basically 10 degrees from the center, which is normal emission. And so we should expect it around 20 degrees, let's say. And so this is what we observed. This is basically our emission at 17 and plus minus, let's say, 17, but very close to 20 degrees. So here is the angular dependence, and this is the threshold behavior. In this case, though, the threshold is much higher, is almost 4 times higher. So actually, we were not able to do the polarizability study because the sample was degraded before we could do the entire polarization. So that is the missing point. So basically, once we published this, we were thinking about, okay, what to do next. And so Ili joined a 4-month research stay in the group of Professor Naihao Cheng in Houston. And the idea was to move from rhodamin B, which is new to being a molecular system we thought to reach quite easily, and we moved to quantum dots, hoping to not only have a more stable system, but also being able to target two photon emission systems. So in this case, instead of pumping the system with a 532 laser, the idea was to pump it with a near infrared laser and having, two photons combining to promote the emission. And the reason here is that in the previous case, when you pump the system at 530 in the, let's say in the low visible and the green, you always also pumping the plasmonic response, the localized response to the particle, and so on and so forth. And so that creates a very complex system. It was very hard for us to understand what was going on. So the idea was to simplify the system, at least from a light matter interaction point of view. So as you can see here, this is the morphological characterization. This is how the sample look like. This is just an AFM to see a little bit the structure. And these are SEM characterization where you can distinguish the silver particles from the quantum dots that are beneath it, underneath it. That we also try to do a cross section. Of course, the quantum dots is, we believe, is 1 or 2 layers of quantum dots. We're not able to find it there to resolve it with the SEM. But again, our SU8 layer, so our thin film to create the wave-guided modes is there, and that is something that we can clearly see here. So once again, here you have the optical characterization with our sharp resonances and our contour plot showing the diffraction line. And this is basically the emission characterization. This is on quantum dots alone. So when you see here, these are just quantum dots without the particles. This is in solution, just to see where the emission is. And here is on the thin film. And this is the angular characterization in emission. In this case, is the detector is always normal to the sample. So what we're doing is twisting the sample. But anyway, what you need to pay attention here is that we don't see any angular dependence as expected, because this is just quantum dots. While when we put the nanoparticles, we try to compare the 1 photon versus the 2 photon emission system. So on the top, you have the 1 photon, so 515 excitation. Very simple. We excited at 515, we excite the quantum dots emit. And this process is mediated by the presence of the metasurface. So as you can see here, there is an angle dependence. So we can modify, we see a modification of the emission. While when we go at the 1030 excitation, so in this case we have a 2 photon process. Again, we see a modulation, and the emission is much sharper. And again, we believe this is due to the fact that here we are also exciting. There's also all the plasmonic components and all the components of the quantum dots are excited at the same time. So this is a much more complicated line metric interaction, and here instead it's at 1030 we can actually also go at much higher power in terms of excitation, in the sense that here at 515, if we go above this, we burn the system immediately, while in this case, since we're not exciting the localized plasma, we're not generating heat, so on and so forth, the system is much more stable. These are preliminary results. It's actually the first time I present them. I thought this was a good occasion to get some feedback on this. So here I don't have a very clear explanation for everything that we see here. We miss theoretical simulations and to a little bit understand what is going on. But yeah, we are excited about this because we can definitely see a role of the plasmonic metasurface on the emission of these quantum dots in a non-linear process, so in a 2 photon process. So the conclusions here is that basically what we have been, our contributions here is that we show that colloidal system can be used to generate high quality factor lattice resonances. So this has definitely a space within this field where you can produce very high quality factor resonances using hard lithography, so-called hard lithography. But this takes away all the control over the crystallography and the composition of the system. And so we think that these colloidal metasurfaces can have an impact in certain direction, because we can tune the internal structure of the repeating unit in a much more controlled way. I showed you basically 2 different systems. One, we were changing simply the size of the nanoparticle, and then one, the composition. And then we successfully also demonstrated that these structures have enough quality to promote nonlinear optical phenomena, such as lasing or 2 photon emission. And then I always like to remind that this is all done with exposed cavity. So one line of research that we are thinking about now is that since we have an exposed cavity, we can make this metasurface interact with the chemical space. And so this opens some interesting direction for bioimaging, sensing, or even photocatalysis. So I will, for the last part of the talk, I think I still have a little bit of time. I want to switch a little bit here, and this is a different, completely different approach, because of course this is all great. I hope I convinced you that I like self-assembly. I've been working on that for quite some time, and I think there is still a lot to do and things to learn and to improve. But if we are honest with ourselves and we look at the system, when we say, well, we synthesize the particle, then we dry them, understand, and that's it, we get down with the surface, it's not really that simple. Because we need to do a synthesis that generally require purification, concentration, and ligand exchange. And generally these concentrations means, centrifugation steps. And then we do the sub-assembly. And all these steps need to be optimized, and all these steps have a lot of problem because we always have to be very careful about the colloidal stability of the system, okay? So basically, this comes with some drawbacks. So generally, we need to do liter scale synthesis, which is not simple for every single system. These are hard to scale step, because any student that has done centrifugation know what I'm talking about, that when you have to centrifuge 6 liters of particles per pump. And then there is the problem that these are all very delicate conditions. So basically, you always have to do an ad hoc optimization for every single system. And then if someone comes down, typically physicists come down and like, I don't like gold, I want silver, and I don't like it to be, I want rods that are a little bit longer. You're like, sure. And now I have to re-optimize everything so for that system to work. And so basically, if we want to abstract this a little bit, what self-assembly is I create my raw material and then I assemble them on the surface, and it's very, very hard in the moment that you go from one system to a more complicated system to really control and have a functional device. So as I show you, for example, in the second example that I show where we co-assemble gold and silver nanoparticles, of course, I'm not able to say I want 50% gold, 50% silver in every single repeating unit. I cannot say I want the gold in the center and the silver around it. That is extremely complicated to do. So an approach that would be a little more rational is saying, okay, like why I cannot start from the surface and then create my repeating unit from bottom up directly on the surface. So doing a pattern in situ growth approach. Okay, so this would be basically keeping the surface always fully functional, having complete control on every repeating unit, and being able to customize it as much as I want. So that's the dream. How do we do this? So the benefits, a little bit more on benefits, I always forget the slides, is that not only we can theoretically translate everything we know from colloidal synthesis directly to the substrate, okay? But so we can control the morphology, we can control the crystallography. There are two important additional benefits, which is that we can control the growth pattern and the orientation. So we can make our particle grow in different patterns, okay? If we are able to do what I'm proposing, okay? So if the idea come true. And then we can control the orientation. So theoretically, I am also capable of controlling the orientation of every single particle that I'm growing with respect to the substrate, right? And the other very important thing is that it opens up completely new possibilities for interacting, for controlling the interface between my nanoparticle growing system and the underneath material, which is something that is really hard to do with self-assembly, because typically when we're dealing with colloids, we have a ligand shell, and that ligand shell will always be present between my particles and the substrate. So what do we know about in situ growth? What we know about in situ growth is basically that it is hard, very hard, and that people have tried it for many, many years. I mean, as you can see, there are papers that dates back to almost 20 years now, but has always remained a very niche field where always the question is, why do you want to grow something so ugly on the surface when you can grow so beautiful particles in solution? So it has been looked into, but never too detailed, in too many details. And the conclusion of I put these examples here for a reason. The first one is that we do observe the possibility. There have been some studies where show that by changing the growth, we can control very poorly, but we can control which kind of particle we observe. So to a certain extent, it has been shown that the same kind of control that we show in colloidal solution is at least theoretically possible on in situ growth system. In this study, this is very interesting because they used basically these conditions that in solution would give you cubes, and instead they obtain triangles, which tells us that what we learned in colloidal solution is not necessarily 100% translatable to in situ growth. And this is a study that I liked a lot because here you see they presented this paper as a forest of nanowire. And this is a clear example of basically what gets me most excited about in situ growth, which is that there are structures that you can grow in situ that you will never be able to grow in solution. So if I grow nanowire in solution, no matter what you do, you will never get this, ever. So there is a space where in growth can bring new player on the table, can give us new system to play with, okay? And the other thing that you need to know about in situ growth, and that makes it extremely hard, is that you always have a moment where you have your material where you want to grow your particles, and you have to expose it to a solution containing all the chemical elements that you need for the growth. So you always have to be aware that you need to control and possibly avoid what we call secondary nucleation or homogeneous nucleation. Basically, you have to, if you want to control what you have on your sample, you have to make sure that the particle that you have on the substrate grow directly on the substrate, and they are not growing in solution and then depositing on the substrate. Otherwise, you're not controlling them. So this is controlling on secondary nucleation is probably one of the most complicated things. So the challenges of in situ growth are to regulate the nucleation density, the reason why it hasn't been studied that much. So if you look at all the literature, these are basically the three main challenges. We cannot regulate the nucleation density, so we cannot tell our system, you need to nucleate a particle here, here, here. They just nucleate everywhere. It's very hard to control the chemical environment because there is the chemical environment include the substrate. Okay, so every substrate is different. And it's not as homogeneous as a solution. So the substrate, if you have a substrate, it's not identical here, 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 unless you're really careful how you fabricate the sample. And then you have to suppress secondary nucleation, as I just mentioned. And so the approach that we proposed, we called it chemical contrast in situ growth. But basically, the idea is, okay, let's use soft lithography. So every technique that we learn, we do in the self-assembly, basically. But instead of using it to assemble particle, we approach it to change the chemical composition of the substrate. So what we wanted to do is to create a substrate where you have two different surface chemistry. One surface chemistry good for particle growth, the other surface chemistry bad for particle growth. So basically the idea is that I create this and then I expose it to a growth solution. My particle will be able to nucleate and grow only at surface one. So theoretically, this is what I should get. All right. Again, this is the pretty picture. So in the proof of concept, this is basically in one step and no fancy, going away from fancy rendering. This is what we want, right? So we want something like this, and we want to expose it to the growth solution and get the particle. And so Ilya and Gail basically teamed up together, and this is what they managed, the approach that we managed to come up with. And the idea is we use hydroxypropyl cellulose, which is a polymer that is thermodeformable and that it can be washed out with water. We spin coat it, and then we use a stamp to make holes in it. Okay, so then we etch the residual layer so that we got basically a fishnet with holes. So we expose the PMS underneath, and then we apply this ink. And the reason we chose this ink is that there is this chemical bond, which is a reducing chemical bond, and we know that this can nucleate particles. Then we remove the HPC. As I said, this can be removed by simply exposing the substrate in water, and this is what we got, right? In theory. And then we got the particles. Okay, so let's focus on the first step. So creating basically this fishnet of HPC. So this is basically the same process I just explained, just reiterated there, and this is what we got. Okay, so we show that we can create HPC stencil or fishnet that you want to call with different lattice parameters, and these are actually extremely thin. These are 30 to 40 nanometer thin. I don't know if there are some experts in nanoprint lithography here, but normally when I say that these are even we can get down to 30, 40 nanometer thick, they look at me with a very weird and ugly face because they're like, that's not possible, which is true. because if you do this on a silicon substrate, you will never be able to make something so thin. Because you basically, when you use a stamp and you press to deform your HPC, the cellulose needs to fill up the stamp. And so if you don't have enough material to fill up the stamp, okay, it will be filled unevenly. So you will have areas where the HPC goes up and the other areas where it doesn't. And so your fission will turn out like this. So very bad. But that's why we used a PDMS substrate, which is a soft substrate. And so we were able to go as thin as 30 nanometer, as confirmed here by this TM. So the idea that we have in mind here is that when you have a soft substrate, you can actually press very, very hard and basically convince your HPC, your cellulose to fill your gaps, okay, in an even way. So that said, we basically selected one. We didn't select at the end of the 30 nanometer because this is water soluble. So it's a good thing because I can simply wash it by dip it in water. But it's a bad thing because if you have a humid day in the lab, 30 nanometer, you take it out and then you just like by looking at it, it's gone. If you breathe too hard, it's gone. So we actually ended up staying on 130, 150 nanometer, which gives us a little bit of time to work. And the other good thing, sorry, that it's important to mention is that here you see there's no residual layer or very minimum residual layer. And this actually is extremely nice because we don't have to do a reactive ion etching step to eliminate the residual layer. But actually we only do a reveal zone of 30 seconds to make sure that we expose the surface. Then we apply by spin coating, we apply our chemical ink, and then we remove the HPC by water, and we're ready to grow the particles. These, of course, didn't work at all because, as I said, we need to control the secondary nucleation. So the way we control the secondary nucleation is we play around with the composition of the surface. I'm not going to go into the detail here, but basically we try to identify condition where for at least, so these are basically UV visible done on the solution. And we try to identify conditions where at least for 10 minutes, we were not able to see any nucleation in solution. And then we chose those conditions and then we stopped the growth at 5 minutes. So that was our idea. And that by magic turned out that we could finally observe some patterning. And this has recently been improved by Pau, which is another master student that joined the group. And so now we can see here in the zoomed that we can start to see single particles start to control it a little bit better. But again, we got very excited about this. And so we started to see, okay, how can we control the system? So the first thing was, of course, let's grow it for different amount of time. And so we saw that by growing it for less, by exposing our substrate for less time to the growth solution, we can go down to basically 50 nanometer. We recently tried to do, for those of you that have some knowledge of, like some experience with the colloidal synthesis, we tried to change the pH of the solution. So we use acidic condition. In those conditions, we were able to slow down the growth a little bit. And we were actually able to get this down to 20, 25 nanometer. Which start to be very interesting because when you start to get down to very small particle, you can show we were able to show that we could modify it. So do a second growth step on the very same substrate and go in this case from sphere to stars. So again, this is promising in our vision in order to start to apply all the growth that we know how to do in solution on the substrate. So this is basically. This is a good thing when you have students to work for you. Gail and Ili spend a lot of time looking at SEM pictures and counting particles and so on and so forth. Fortunately, I didn't have to do it because this has been very daunting. But here is basically a little bit of statistics on the substrate that we grow. Because I'm sure that by looking at this picture, you're like, yeah, I can see a pattern, but it's not very beautiful. It's not perfect as the one you showed us before. It's true. But if we do some statistics, we basically show here in green. I took the one that I think is most important, which is when we grow, we basically have over 90% of the particles are actually in the pattern. So we basically confirm that we are not just seeing the pattern where there is no pattern. These are basically all the particles that we observe in the CM are grown in the pattern. And the other thing that makes me really interested about the system moving forward is that we only observe 2 particles per region in average. Why that is interesting? It is interesting because if you see here, these circles represent the area where theoretically we have our reducing agents. And as you can see, these areas are 230 nanometer in diameter. So theoretically, the particles that we're growing are much smaller than the area. So what this tells me is that once a particle nucleate, it is much more probable for this particle to grow than from other particle to nucleate in the same spot. So the idea here is that if instead of 230 nanometer, I can reduce this to, I don't know, 80, 50, which should be doable using our approach. Theoretically, we will be able to control better, the position of the particle, because now the particle can nucleate in any point in this area. But if I reduce the area, I will control it better. Okay, so finally, just this is something that is important because I told you all the story telling you that we can make metasurfaces. So are these metasurfaces? So to do that, we did our standard optical characterization, and indeed we see the presence of a lattice resonance. That is, I was very surprised because the system is not extremely perfect as so the defect in the system will have a detrimental effect on your collective response. But indeed, we were able to observe these lattice resonances and see how they change with the angle, as I showed you for the previous project. So yes, we were able to access sort of sharp lattice resonances for a system that was completely grown in situ. And so we are really excited about this. And I think that moving forward, there is really a lot of work to do, which is basically the idea at the base of NanoGrow Direct, which is the ERC starting project. Since there are a lot of students, just a little bit of publicity, because we will be hiring very soon. The lab in Cantabria will start in probably September, October, so within a new cycle. And yeah, we will be hiring both students and postdocs. So if someone is interested, please drop me an email. But yeah, basically the idea is to exploit this. So the conceptual idea of the starting grant is we have the possibility to grow particle on surface in pattern. How can we exploit this to make it where to basically obtain metasurfaces that they would not be possible to make using colloidal subassembly or other type of approaches. So with that, I just conclude with acknowledgements. I mean, all the nanopter family at ICMAV, and specific more than ever, I thank Ili, Bao, and Gail, which basically did most of the hard work for the that I presented today. Of course, the collaborators and people that give us money to play, which is always nice. So thank you very much for your attention, being here today. Thank you, Juan, again for the invitation, and please, questions.
Thanks a lot, Leo. Very interesting. I'm sure there are a lot of questions. Anyone wants to start? Okay, I will start. I have several models, but
Sure you.
I mean, let's start with the basic question. I mean, in terms of applications for a biosensor like a evanescent wave sensor, which of the strategies you think are the more interesting, exploiting local plasmonic resonance or lattice plasmonic resonance?
That's a good question. So the problem that I see here is that if we use colloidal system when you do biosensing, the main problem that I see that actually we discussed before the talk is that you need to make sure that under your analytic condition, your system doesn't react or doesn't move, in the sense that you need your lattice to be very stable. You need in order to see it move. But in principle, if you can guarantee that your particles are not going to move away, okay, and so destroy your lattice, theoretically having a very sharp resonance, you should be able to see a shift. So do a better sensing, a more sensitive sensing compared to
because the Q factor is high.
Exactly, the Q factor is higher, the resonance is sharper, so the shift would be easier to spot. That said, there's a lot of work to do in terms of functionalizing these things. We tried, actually, we were very surprised. So that we did a very simple experiment in that sense with our metasurfaces, which was simply flowing on top of the assembled metasurface different solvents. Well, basically water with different concentration of ethylene glycol to change their refractive index, and they seem to be pretty stable. But the quality factor, I mean, all in all, when we got down to the the typical RU figure of merit for your sensor. They are not extremely better, so the improvement is still not as high as it should be for compared to Biocore, especially. But it is true that we didn't use a very complex detection system like Biocore, right? Where they have the prism at the bottom, they do a evanescent wave, and then so we use a very simple microscope and so there is room for improvements there.
Questions?
When you talk about these assemblies made with different particle sizes, and you talk that there's different happening, what is the effect of the ligand?
Good question. Basically, the idea would be that if you have a longer ligand, so you space the particle, you reduce the near field coupling, you reduce the optical losses, you get better processes. That is in a nutshell. Practically doing it with a soft ligand, since they are assembled, it's not that easy to say, okay, instead of using a PEG 2000, I use a PEG 800. Not as easy. So what we were trying to do is to use an inorganic shell, so it goes silica on top, but it's more easier said than done. So basically, we can make the spheres, we can make the silica shell, but it cannot be too big. So there's always the eternal problem of growing a 20 nanometer silica shell. It's not easy. We managed to get something like 50 nanometer, 30 nanometer silica shell, but then assembling them is. Yeah. I mean, it was, but not. The thing is, like, you cannot compare in the sense, right? It's let's try to explain. The assembly is so much worse than the particle by themselves that even if the particle inside the cluster are more spaced, anyway, the optical properties are worse. And so that you cannot make a direct comparison. Ideally, what we would like to do is being able to assemble the particle and then somehow separate them within the cluster directly. So you see the same spot, the same sample, and you see the optical properties change. So it's always very hard to make a fair comparison, right? So with silica, we didn't manage to do it. And absolutely.
Maybe polymer?
Can be.
Hydrophobic and hydrophilic?
Yeah. That's a possibility. But yeah, again, please come back to the problem of every time that you go from PEG to a block of polymer, like you have to redo the entire optimization of the system. So at the end of the day is, again, how many students can you sacrifice to the altar of doing that? But yeah, no, it's theoretically it's possible. Yeah, but that would definitely improve the optical properties for sure.
Okay.
Questions? Yeah.
With certain pattern, can you make the object invisible?
Yeah. Yeah, you can do it. Yes. If you can design your structure, these metasurfaces can be used for cloaking. So in theory, it is possible. But generally for cloaking, since it is there's no chemistry involved, let's put it that way. I don't think that this system will be better than an evaporated, surface, because of course, in terms of identity of each repeating units and in terms of defects on your surface, doing an evaporation will always result in a better results from that point of view. So if you're not interested in very large scale devices, or if you're not interested in any kind of dynamic interaction with the environment, I really think that evaporation will, at least at the moment, probably still be the leading approach. I don't think we are not there. We cannot compete with that.
Connected to this question of comparing evaporation and solution process, in terms of structural stability, which differences you mean?
Structural, you mean to?
In the sense that how how it evolves in time. I mean,
it
still evolves, I guess, in time. No? It's not fully
So it depends. So the gold, the self-assembled gold structure, or even the silver one that Ely use, since they are passivated with PEG, they don't oxidize that easily. They're actually quite stable for quite a long time.
But that, I don't mean so much oxidation, but whether there is still an evolution of the crystal growth when you do it from solution, or you sort of see a saturation and that's it.
In the moment that you stop the growth by taking the sample out of the solution, the sample is grown unless you expose it to another growth solution, but that's on purpose. So the system is stable. Of course, for example, in the case of nanostars, I don't expect them to be stable forever, but that's because they reshape, but that's what they normally do. So basically, again, you basically start importing all the knowledge that you have from the colloidal system to the in situ. The problem that we are facing in situ is the characterization, because of course we cannot use TEM, so that is complicated. So it's much harder to monitor this type of evolutions and stability, but we're working on it, coming up with a few ideas to try to understand better the system overall. But I think that for example, in terms of the problem is always oxidation for us, because at the nanoscale they tend to oxidize very quickly, especially if you're talking about silver. Over there, another interesting thing that I think that this system can be beneficial compared to others, compared to self-assembly or evaporations, that you can really, like, if these particles grow at the interface, you can play with the underneath substrate to also prevent or the chemical modification of the substrate. That's what really interested me. So for example, you can think about, if I can replicate this in situ growth system on a conductive substrate, whatever that is, theoretically, I can start combining electrochemistry and chemistry for the growth of the particle. And that opens basically a new direction that you cannot do in solution. In solution, you can never apply voltage to a particle, but there you can. The particle will be on the surface and you can modify it. That's, for example, is interesting. So there's a lot of pros and cons. And I think that where this system has to go is basically target structures that cannot be prepared in any other way. So of course, if we stay with the idea of making, disk, I mean, do it for evaporation. I mean, this is one way more complicated otherwise.
More questions? Yeah.
Hello. I was wondering around the size distribution that you have on the solid method, not on the solution one, because you have several nanoparticles, and how that
is this one, right?
Yeah, exactly. Like, I suppose that also the students that were looking probably measure them, and they are quite different between them. No, the size distribution are so different, and how that affects the spectrum.
Yeah. So. Totally true. That affects in the sense that everything that deviates from a perfect array, where you have the exact same identical particle repeated over and over again, makes your optical properties worse from that point of view. Now, this system is very far from perfect, but there's two considerations here that I think are important to make. The first one is that for the moment, we focused. We didn't do anything to control the quality of the particle that we're growing. So the system has been just optimized for not having secondary nucleation. And that was really the turning point. We have worked on this for about 7 months, and we were not getting any kind of pattern. And then once we managed to avoid secondary nucleation, the pattern emerged. And so the one thing to keep in mind is that there is a lot of work to do to make the particle better and more uniform. Okay, so we haven't done anything. So this growth solution is just gold precursor, ascorbic acid that is the reducing agent, and a surfactant at random concentrations. So there's been really zero optimization. So what makes me think that there's ample room for improvement. And the second thing that is important to mention is that if you look at the products that you mentioned here that are actually different one from the other, you see spheres, you see triangles, you see truncated triangles and platelets, and you see rods. And these are basically exactly the type of particle that you would expect from a bed colloidal growth. So if you go back to the first paper about colloidal synthesis, this is exactly the kind of product that you would see that they were not controlling. So this tells me that this system is, at least to a certain extent, behaving in a way that we understand, and that's predicted for us. And so I think that we can improve it. We have actually done, so Gail now is working in San Sebastian, and she kept working on in situ, even though not in a pattern way. She's just growing particles in situ. And yeah, we're starting to understand a little bit better how to grow particles and how to control their size and shapes and so on. And yeah, it's not easy, as I said, mainly because of the characterization. So we don't have the TEM tool where you can really look at the details of the particle. And an SEM, when you go below 20 nanometer, it's complicated to tell if it's a sphere, if it's a cube, if it's really, really hard. And so that is actually right now the main problem that we're having. That's the main problem that we need to solve. I think that if we crack the characterization and understand what we are seeing, then we are on the good track to actually make this interesting in terms of growing identical particles.
Okay, if there are no more questions. Oh, okay, another question.
You were talking about the quantum dots. I think you just got me solenoid.
Yes.
Did you try with that type of quantum dots?
No, actually, the main problem of that project is that we cannot make a quantum dot, so we had to buy it, which is very limiting in terms of the quality, in terms of the money, and in terms of the type of quantum dots that you can do. Actually, I think that the system will be much better if we can even move a little more, because this emits at 620, and at 620 you still have a little bit of the localized response of each cluster. So it would be very interesting to move even more to the red, where you don't have anything coming out from the single unit. And so the only plasmonics there comes out from the lattice resonances. I also have to mention that almost, I would say 99% of the work done on plasmonic metasurfaces on 2-photon emission, they always match the lattice response with the fundamental excitation. So in our case, it would be put a lattice resonance is at 1030. Instead, what they do is basically modulating the 2-photon absorption. While in our case, we are putting the lattice on the emission. So we're trying something slightly different. And we don't understand really the system very well yet. These are very preliminary results. But yeah, that's a very good point. It would be very interesting to have better quantum dots and also more than 25 milligrams to work with. Yeah.
More questions? Well, thank you very much, Leo.
Thank you guys.